Hello dear students, glad to meet you again in this session. In this session 1.12, we are going to discuss about redox reactions from chapter 1, some basic concepts of chemistry in grade 11. In session 1.1, we have discussed about some importance of chemistry, nature of matter and its classification. In session 1.2, we have discussed the 7 basic units of SI system. In session 1.3, we have discussed the physical quantitative properties of matter. In session 1.4, we have discussed the uncertainty in measurements. In session 1.5, we have discussed the laws of chemical combination. In session 1.6, we have discussed the postulates of Dalton's atomic theory, atomic mass, molecular mass, and formula mass. In session 1.7, we discussed mole concept, Avogadro number, molar mass, and molar volume. In session 1.8, we have discussed gram equivalent mass for oxidizing and reducing agent and for acids and base. In session 1.9, we have discussed the molecular and empirical formula. In session 1.10, we discussed stoichiometry and its calculations. In session 1.11, we have discussed the methods to express the concentrations in chemical solutions. Learning outcomes. Students, at the end of this session 1.12, you will be able to define oxidation and reduction reaction, list different concepts of redox reaction, compute oxidation number, and list the rules of oxidation number. When an apple is cut, it turns into brown after some time. Do you know the reason for this color change? It is because of a chemical reaction called oxidation. Burning of LPG gas, rusting of iron, oxidation of carbohydrates and lipids to get energy, or some of the oxidation reaction we come across in our daily life. All oxidation reactions are accompanied by reduction reactions and vice versa. Such reactions are called redox reactions. First, let us see about oxidation. Classical concept of oxidation. Addition of oxygen or removal of hydrogen is called oxidation. Consider the following two reactions. In reaction 1, iron reacts with oxygen in the atmosphere and form iron oxide. Here, oxygen adds to the metal which is responsible for the rusting of iron. So, addition of oxygen is called oxidation. In reaction 2, hydrogen sulphide reacts with chlorine to form hydrochloride and sulfur. Here, hydrogen is removed from hydrogen sulfide. Here, hydrogen is removed in this reaction. So, removal of hydrogen is also called oxidation. Reduction reaction. Reduction reaction is quite opposite to that of the oxidation reaction. Let us see the classical concept of the reduction reaction. Addition of hydrogen or removal of oxygen is called reduction reaction. Consider the following two reactions. In reaction 1, that is the reaction between the cupric oxide and carbon, oxygen is removed from cupric oxide. Cupric oxide here reduced to copper. Since oxygen is removed, we call this reaction as a reduction reaction. In the second reaction, the reaction between sulfur and hydrogen, hydrogen is added to sulfur to form hydrogen sulfide. Since addition of hydrogen takes place in this reaction is also an example for an reduction reaction. Electronic concept of redox reaction. Students, there are some redox reactions in which oxygen or hydrogen are not associated with that reaction. For such reaction, we can explain the process on the basis of electrons. The reaction involving loss of electron is termed as oxidation, and the reaction involving gain of electron is termed as reduction. During redox reaction, the element which gains electron will gain energy and it will become a high energy element, and the element which loses its electron loses its energy, so it will become a low energy element. Consider the following two reactions. In the first reaction, ferrous ion loses one electron and becomes ferric ion. Since it loses one electron, Fe2 plus ion becomes Fe3 plus ion. We can say ferrous ion oxidized to ferric ion since it loses one electron. In the second reaction, copper 2 plus ion gains 2 electron and forms copper atom. Here in this reaction, since it gains 2 electron, the charge on copper 2 plus ion gets neutralized and it is reduced to copper atom. So we can say copper 2 plus ion gets reduced to copper. The next concept is the oxidation number or the oxidation state definition. The imaginary charge left on the atom when all the atoms of the compound have been removed in their usual oxidation states that are assigned according to the set of rules. Here I have taken a simple compound as an example, sodium chloride. The imaginary charge left on the atom. For example, the imaginary charge left on the atom sodium, in our case, when all the atoms of the compound that we have taken is sodium chloride here. Here, since it is a simple compound, the other atom is chloride here, right? So if we remove chlorine along with its oxidation state, the imaginary charge of sodium is what? +1. So +1 is the oxidation state or the oxidation number of sodium in sodium chloride. To calculate the oxidation number or the oxidation state of an atom, we have some set of rules. Let us see the set of rules one by one. Rules of oxidation number or oxidation state. Let us see the first rule. The oxidation state of a free element. Free element means it should be in the uncombined state is 0. So for example, each atom in hydrogen molecule or chlorine molecule or sodium or sulfurate have the oxidation number of 0. When you take sodium metal alone, sodium element only present in sodium metal, right? So the oxidation state of sodium here is 0. Rule number 2, for a monoatomic ion, mono means single, atomic ion means charged particle. The oxidation state is equal to the net charge on the ion. I have taken sodium chloride. Sodium has 1 electron in its outermost orbit, so it has the tendency to transfer 1 electron, and chlorine has 7 electrons in its outermost orbit, so it has the tendency to accept 1 electron. Since sodium donates 1 electron, it becomes Na+, and chlorine accept 1 electron, it becomes Cl-. The oxidation state of the monoatomic ion Na+ is +1, and the oxidation state of a monoatomic ion Cl- is -1. Rule 3a, the algebraic sum of oxidation states of all atoms in a molecule is equal to 0. Here I have taken sulfuric acid. In sulfuric acid, we have 2 hydrogen atoms, so 2 into oxidation number of hydrogen, 1 sulfur atom, so plus 1 into oxidation number of sulfur, and 4 oxygen atoms, so plus 4 into oxidation number of oxygen. When you add all these oxidation numbers of the atoms present in sulfuric acid, the algebraic sum of the oxidation state of all these atoms in a molecule is equal to 0. Rule 3b, the algebraic sum of oxidation states of all atoms in ions is equal to the net charge on the ion. For example, I have taken sulfate ion and the charge of sulfate is -2. What are all the atoms present in sulfate ion? Sulfur and oxygen. So when we add the oxidation number of sulfur and oxygen ion in sulfate, that is 1 into the oxidation number of sulfur, plus we have 4 oxygen, so 4 into oxidation number of oxygen, it will be equal to -2 since the net charge of sulfate is -2. Let us understand the rule 3a and 3b by calculating the oxidation number of sulfur. First, let us calculate the oxidation number of sulfur in sulfuric acid. Let us assume the oxidation number of sulfur as X. We have 2 hydrogens, so 2 into oxidation number of hydrogen is +1, so +1 plus X, plus we have 4 oxygen atoms, so 4 into -2 equal to 0, because we know that the algebraic sum of the oxidation state of all the atoms in a molecule is equal to 0. So 2 into +1, 2 plus X, 4 into -2 is -8 equal to 0. When this -8 come to the right hand side, it becomes +8, and this +2 will become -2 when it comes to the right hand side. So 8 minus 2 is equal to 6. So X equal to +6, which is the oxidation number of sulfur in sulfuric acid. Now let us calculate the oxidation number of sulfur in sulfate ion. Let us assume the oxidation number of sulfur as X plus, we have 4 oxygen atoms, so 4 into oxidation number of oxygen is -2, so 4 into -2 equal to -2, because we know that the oxidation number of all the atoms in an ion is equal to the net charge of the ion. So here X 4 into -2 -8 equal to -2. When this -8 comes to the right hand side, it will become +8. So 8 minus 2 is equal to 6. So X is equal to 6, which is the value of the oxidation number of sulfur in sulfate ion. Rule 4a, hydrogen has an oxidation number of +1 in all its compounds, but it has exception that we will see in rule 4b. Here we have taken hydrogen chloride as an example. Hydrogen has 1 electron in its orbit, so it has the tendency to give 1 electron to become stable. Chlorine has 7 electrons in its outermost orbit, so it has the tendency to accept 1 electron to become stable. In hydrogen chloride, though it looks like a sharing of bonding electrons, it is not a complete covalent bond. Since chlorine is highly electronegative, the bonding electrons are very near to chlorine when compared to hydrogen. So, bonding electrons share unequally between two atoms, and this exhibit a partial charge on the atom. So, chlorine possesses a partial negative charge and hydrogen possesses a partial positive charge. So, the bond is a polar covalent bond. Since hydrogen contributes 1 electron, the oxidation number of hydrogen in hydrochloride is +1. Rule 4b. Hydrogen has an oxidation number -1 in metal hydrides. This is an exceptional case. Usually metals are electropositive. We know that sodium has 1 electron in its outermost orbit, so it has the tendency to donate 1 electron to become stable. We know the atomic number of hydrogen is 1 and hydrogen has 1 electron in its orbit. In this case, hydrogen accepts 1 electron from sodium to become stable. Since hydrogen accepts 1 electron in metal hydrides, it attains a negative charge. So, the oxidation number of hydrogen in metal hydrides is -1. Rule 5. Fluorine has an oxidation state of -1 in all its compound. As we have seen in hydrogen chloride, the bond in hydrogen fluoride is also a polar covalent bond. Since fluorine is a highly electronegative element, the bonding electron shared between these two atoms are unequally shared and exhibit a partial charges on atoms. So, fluorine possesses a partial negative charge in hydrogen fluoride, and hydrogen possesses a partial positive charge in hydrogen fluoride. Since fluorine accepts 1 electron from hydrogen, the oxidation state of fluorine is -1. Rule 6a, the oxidation state of oxygen in most of the compound is -2. Let us take water as an example. If we assume the oxidation state of oxygen is X in water molecule, we have 2 hydrogen molecules, so 2 into +1, which is the oxidation number of hydrogen. 2 into +1 plus X equal to 0, because we know that the algebraic sum of the oxidation state of all the atoms in a molecule equal to 0. 2 into 1, 2 plus X equal to 0, which gives the value of X equal to -2, which is the oxidation state of oxygen in water molecule. There are some exceptions in the oxidation state of oxygen. They are the oxidation state of oxygen in peroxides, superoxides, and compounds with fluorides. First, let us see about peroxides. For this, let us take hydrogen peroxide as an example and assume the oxidation state of oxygen as X. Here in hydrogen peroxide, we have 2 hydrogens. So 2 into +1, which is the oxidation number of hydrogen, plus we have 2 oxygens. So 2 into X equal to 0. We know that the algebraic sum of the oxidation state of all the atoms in a molecule equal to 0. We have 0 in the right hand side. Now 2 into 1, 2 plus 2X equal to 0. Now 2x equal to, when this plus 2 goes to the right hand side, it will come as minus 2. So 2x equal to minus 2, which gives the value of x equal to minus 1, which is the oxidation number of oxygen in peroxide. Let us calculate the oxidation number of oxygen in superoxides. For this, let us take potassium superoxide as an example. Assume the oxidation number of oxygen as X. We have 1 potassium, so 1 into oxidation number of potassium is plus 1. So 1 into plus 1 plus, we have 2 oxygen over here. So 2 into X is equal to, we know the algebraic sum of the atomic state of all the atoms present in a molecule is 0. So equal to 0. That gives 1 into 1 gives 1 plus 2x equal to 0. When this one goes to the right hand side, we get 2x equal to minus 1, which gives the value of x as minus 1 by 2, which is the oxidation number of oxygen in superoxides. Let us calculate the oxidation number of oxygen in compounds with fluorine. For this, let us take oxygen difluoride as an example. Consider the oxidation number of oxygen as X plus, we have 2 fluorine here, so plus 2 into minus 1. Minus 1 is the oxidation number of fluorine. X plus 2 into minus 1 equal to 0, because we know that the sum of the oxidation state of all the atoms in a molecule is 0. Here x plus 2 into minus 1 is minus 2. So x minus 2 equal to 0, which gives the value of x as plus 2. So the oxidation number of oxygen is plus 2 in the case of oxygen difluoride. Rule 7a. Alkali metals have an oxidation state of plus 1 in all their compounds. We will study about these alkali metals like lithium, sodium, potassium, rubidium, cesium, and francium under the concept periodic classification of elements in detail. Now let us take sodium oxide as an example. As we know, sodium has 1 electron in its outermost orbit. It has the tendency to donate that electron. Here in sodium oxide, we have 2 sodium and each sodium donates 1 electron to oxygen. Since sodium donates 1 electron, the oxidation state of sodium is plus 1 here. So the alkali metals have the oxidation state plus 1 in all their compounds. Rule 7b. Alkaline earth metals have an oxidation state of plus 2 in all their compounds. Like alkali metals, we have alkaline earth metals like beryllium, magnesium, calcium, strontium, barium, and radium. We will study about these alkaline earth metals under the concept periodic classification of elements. So magnesium is also an alkali earth metal. So I have taken magnesium oxide as an example. Magnesium has 2 electrons in its outermost orbit. So it has the tendency to transfer those 2 electrons to oxygen in magnesium oxide to become stable. Since it donates 2 electrons, the oxidation state of magnesium is plus 2 in this compound. So alkaline earth metals have an oxidation state of plus 2 in all their compounds. Let us calculate the oxidation number of the elements given in the table from the compounds given in this table. For this, let us consider the oxidation number of the given elements given in this table as X and calculate its oxidation number. First, let us calculate the oxidation number of carbon in carbon dioxide. We keep the oxidation number of carbon as X plus, we have 2 oxygen, so 2 into minus 2 equal to 0, because we know that the algebraic sum of the oxidation states of all the atoms present in a molecule equal to 0. So X plus 2 into minus 2 minus 4. So x minus 4 equal to 0. So the value of x is equal to plus 4 for carbon in this compound carbon dioxide. Now let us calculate the oxidation number of sulfur in sulfuric acid. We know that the algebraic sum of the oxidation number of all the atoms in a molecule is 0. So we have taken 0 in the right hand side. We have 2 hydrogens. So 2 into plus 1 plus X, plus we have 4 oxygen. So 4 into minus 2 equal to 0. 2 into 1, 2 plus X. 4 into minus 2 minus 8 equal to 0. When this minus 8 goes to the right hand side, it becomes plus 8. And this plus 2, when it goes to the right hand side, it will become minus 2. So 8 minus 2, 6. So this gives the oxidation number of sulfur as plus 6 in sulfuric acid. Let us calculate the oxidation state of chromium in dichromate ion by assuming the oxidation state of chromium as X. We have 2 chromium, so 2 into X plus 7 oxygen atoms. So 7 into minus 2 equal to minus 2, because we know that the algebraic sum of all the atoms present in the ion is equal to the net charge of the ion. Here 2x equal to 2x minus 2 into 7 minus 14 equal to minus 2. When this minus 14 comes to the right hand side, plus 14. So plus 14 minus 2, 12. So 2x equal to 12. So x equal to plus 6, which is the oxidation number of chromium in dichromate ion. Now let us find out the oxidation number of carbon in difluoromethane. Let us assume the oxidation number of carbon as X here. X plus, we have 2 hydrogen. So 2 into oxidation number of hydrogen is 1, plus 2 into oxidation number of fluorine is minus 1. So X plus 2 minus 2. So this plus 2 and minus 2 get cancelled. So X equal to 0. So the oxidation number of carbon is 0. Finally, let us find out the oxidation number of sulfur in sulfur dioxide. Here let us assume the oxidation number of sulfur as X. So X plus, we have 2 oxygen, 2 into minus 2 equal to 0, because the sum of the oxidation state of all the atoms in a molecule is 0. So X minus 4 equal to 0. So X equal to plus 4. So this is the oxidation number of sulfur in sulfur dioxide. Redox reactions in terms of oxidation number. During redox reactions, the oxidation number of the element changes. A reaction in which oxidation number of the element increases is called oxidation. A reaction in which oxidation number decreases is called reduction. Let us consider the reaction between potassium permanganate and ferrous sulfate. In this reaction, manganese in potassium permanganate favors the oxidation of ferrous sulfate to ferric sulfate by gaining electrons, thereby gets reduced. If you notice the manganese, the oxidation number plus 7 gets reduced to plus 2. If you notice the oxidation number of iron in ferrous sulfate, it gets increases from plus 2 to plus 3. The reagents which favors oxidation is called oxidizing agent, or we call it as an oxidant. Oxidizing reagents get reduced and facilitate the oxidation reaction. Similarly, the reagents which facilitate reduction by releasing electrons and gets oxidized are called reducing agents. Students, let's recall all the concepts that we have discussed in this session. We have discussed the definition of oxidation and reduction reaction. We have discussed the different concepts, that is the classical and the electronic concepts of redox reaction. We have discussed how to compute the oxidation number. We have discussed the rules of oxidation number and redox reaction in terms of oxidation number. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.